Hello and welcome back, everybody. We're on the worked example section for matrix functions. And in general, I don't think it's actually too complicated as long as you're all satisfied with diagonalization. So I won't get too much into just over and over and inundate you with examples of harder and harder problems. Instead, we'll look at some pretty cool phenomena that occur with these matrix functions, because in some ways, once we have these matrix functions, we can kind of develop an entire matrix calculus. We really have a matrix calculus, which is really exciting. Almost everything you learn in Calculus 1 can be extended to matrices, which is really, really cool. And in fact, in Calculus 3, you're really studying vector calculus, which is the calculus of vector spaces. And all matrices are elements of vector spaces as well, so it kind of goes along with all that. But let's look at a couple really cool examples of this idea of a matrix calculus. The first one I'm going to do is let's consider the matrix 13, 4, 4, and 7, and e to the t m, or e to the t 13, 4, 4, 7. So let's go ahead and compute this. We need to diagonalize. We'll do this as always, where we'll find all eigenvalues. We can get this from the characteristic equation, 13 minus lambda, 4, 4, and 7 minus lambda. That's going to give me 13 minus lambda times 7 minus lambda minus 16. 13 times 7 is a little bit tricky to compute. That's 91. Minus, I've got, so 7 lambda. The inside terms, the outside terms are 13 lambda, and then lambda squared. Then I've got minus 16. And if I combine terms, that's lambda squared minus 20 lambda, and then 91 minus 16 is going to give me 75. It may not look like it, but this is actually factorable. We won't go ahead and try to factor it. We're just going to use the quadratic formula here. The quadratic formula, I look at negative b, that's 20, plus or minus the square root of b squared is 20 squared, will be 400, minus 4ac, so that's minus 4 times 75, all over 2 times a is just all over 2. That's going to be 20 plus or minus the square root. 4 times 75 is 300, so that's the square root of 100 divided by 2. Thankfully, square root of 100 is easily calculable. That's 20 plus or minus 10 divided by 2. And so I've got 30 over 2 is 15, and I have 10 over 2 is 5. So my two eigenvalues are 15 and 5. I then construct the eigenvectors. Which I'm just going to compute as taking 13 minus, so we'll choose lambda is 15 first, 13 minus 15, and then 4, 7 minus 15 on x1, x2 equals 0, 0. That sends me to the matrix, I guess 13 minus 15 is negative 2, 4, 4, and negative 8 on x1, x2 equals 0, 0. Horizontally, I have negative 2x1 plus 4x2 is 0, and I have 4x1 minus 8x2 is 0. Both are telling me the same thing. I could solve the first for x1 pretty easily to find out that x1 is 2 copies of x2. When I find out x1 is 2 copies of x2, that's my relationship, and I have that the vector corresponding to the eigenvalue 15 is x1, x2, and x1 in terms of x2 is 2x2. And I can let both x2's be 1 to recover the eigenvalue corresponding to 15 is 2, 1. So that's associated to lambda equals 15. When I choose lambda equals 5, I have 13 minus 5 is 8, 4, 4, and 7 minus 5 is 2. I have x1, x2 equals 0, 0. The first row sends me to 8x1 plus 4x2 equals 0. And the second row sends me to 4x1 plus 2x2 is 0. Either one can let me write x2 in terms of x1. 2 copies of x1, actually negative 2 copies of x1 is equal to x2. So that's my relationship. I can write that the eigenvector corresponding to 5 is x1, x2, but I know x2 in terms of x1, it's negative 2 copies of x1. Or if I let both x1s be equal to 1, I have that the eigenvector corresponding to 5 is 1, negative 2. And now, having found my eigenvectors and eigenvalues, I can diagonalize. So to diagonalize, my original matrix was 13, 4, 4, 7. This diagonalizes as x, d, x inverse, where x is, of course, formed from my two eigenvectors, 2, 1, and 1, negative 2. So here I'll put 2, 1 in, 1, negative 2 in. And then that multiplies d, which is the diagonal of eigenvalues. My two eigenvalues were 15 and 5. So I have a 15 and a 5 with some zeros. And then I need to calculate x inverse using 1 divided by the determinant. AD is 2 times negative 2, so negative 4, minus BC is 1 times 1, so 1. In other words, I have a 1/5, 1 over negative 5 actually. And then I swap A and D, negative 2 and 2, and I put negative signs by B and C. And if I want, I can cancel all those minus signs at the expense of me adding one more minus sign there. So that's my diagonalization with, in particular, my diagonal matrix right in the middle, which means when I calculate my matrix exponential, I'm just going to be calculating the exponential of the diagonal. So hence e to the t of 13, 4, 4, 7 is going to be x e to the t diagonal, x inverse, or in other words, 2, 1, 1, negative 2, against e to the t 15, 0, 0, e to the t 5. And I always like writing it as 15t and 5t better. So I'll write 15t, 5t, and then I have a 1/5, 2, 1, 1, negative 2. If I want to calculate all of this out, I'm just going to have to do it in 2 steps of matrix multiplications. The first one looking at all my rows against all my columns. The first is going to give me 2 times e to the 15 is 2 e to the 15t, and then I get 1 copy of e to the 5t, I get 1 copy of e to the 15t, and I get negative 2 copies of e to the 5t. This is against to the 1/5, and then the final matrix, 2, 1, 1, negative 2. And I can go through one more round of all rows against all columns. That's going to give me 4 copies of e to the 15t. There's 1/5 coming along for the ride. I have 4 copies of e to the 15t. I also have 1 copy of e to the 5t. I then have 2 copies of e to the 15t and negative 2 copies of e to the 5t. I have 2 copies of e to the 15t and negative 2 copies of e to the 5t. And finally, I have 1 copy of e to the 15t, and negative 2 squared is positive 4 copies of e to the 5t. And so that is going to be my matrix exponential. 13, 4, 4, 7. But actually what I wanted to show was a really cool property of calculus. In calculus, let's evaluate the integral from 0 to infinity of e to the at, minus at actually, dt, when a is positive. And I know a lot of you probably haven't covered what this means. What I mean by this is actually we're going to calculate the limit as x goes to infinity, because I know you've calculated limits of 0 to x, e to the minus at dt. We'll do that in calculus. And so we have a limit sitting around x goes to infinity. We calculate the antiderivative of e to the minus at, that's e to the minus at because it's an exponential, and you divide by the constant coefficient of the variable because of this is coming from u sub. And then you have, because we're evaluating at 0 at x, so this is the limit as x goes to infinity of putting x in e to the minus ax over negative a minus e to the minus a times 0 over negative a. Or if I simplify, e to a 0 power is 1, it's just 1, and then I'm going to let x go to infinity. So long as a is positive, e to the minus ax looks like this. And so when x goes to infinity, the value is 0. So this limit on this term gives me 0, and I end up with negative 1 over negative a, also known as 1 over a, or a inverse. So that's what our integral evaluates to. Let's do the same for our matrix. Let's consider the integral from 0 to infinity of e to the negative t, and then our matrix, which was 13, 4, 4, 7 dt. And you may be wondering about that negative sign when technically we calculated this with a positive sign here. We're just going to replace every t with a negative t. Okay, so I'm going to grab the matrix here, and I'm going to replace every t with a negative t. So I'm going to replace every t with a negative t. Negative, negative, negative. There should have been t there anyway. Negative, 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 negative. I'm going to integrate this from 0 to infinity in t. And it turns out that we can just apply this integral to every entry. So we'll go ahead and apply the integral to every entry, and this gives me 1/5. I have 4 times the integral, 0 to infinity, e to the minus 15t dt, and then I have another integral, 0 to infinity, e to the minus 5t dt. I have 2 copies of the integral, 0 to infinity, e to the minus 15t dt, minus 2 integral 0 to infinity, e to the minus 5t dt. I have 2 copies, integral 0 to infinity, e to the minus 15t dt, minus 2 copies, 0 to infinity, e to the minus 5t dt. I have 1 copy, 0 to infinity, e to the minus 15t dt, and I have 4 copies, integral 0 to infinity, e to the minus 5t dt. Now each of these integrals individually is really just the form, one version of this integral. So I've got a bunch of these integrals on the inside. And we know that each of those just gives 1 divided by the coefficient of the exponent. So we'll go ahead and replace each of those with 1 divided by the coefficient of the exponent. So I'm looking here, 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 here. Those are all 1 divided by the coefficient of exponent. That gives me 4 copies times 1 over 15 plus 1 over 5. So not the negative sign, right? I keep the positive sign there. I have 2 copies of 1 over 15 minus 2 copies of 1 over 5. I have 2 copies of 1 over 15 minus 2 copies of 1 over 5. And I have 1 copy of 1 over 15 plus 4 copies of 1 over 5. We're going to go ahead and simplify this eventually. I still have 1 over 5. And then I have 4 copies of 1/15, and 1/5 is really 3/15. So I'll replace every 1/5 with 3/15 to make my life easier. What do I end up with? I have 4/15 plus 3/15, so I've got 7/15. I have 2 minus 6, I have negative 4/15. I have 2 minus 6 again, negative 4/15. And I have 1 plus 12, I have 13/15. Let's go ahead and pull a 1/15 out to the front. So there's a 5 times 15 there. There's a 1 over 75 here. That's 5 times 15. I have 7, negative 4, and 13. How does this compare to our original matrix, which was 13, 4, 4, 7? Let's take a moment and compare. I think everybody's starting to notice things. What's happened is we've swapped A and D and made B and C negative. Also divided by 75. This should be ringing some bells. What do we suppose the determinant is here? Let's calculate the determinant. This is 13 times 7 minus 16 is 91 minus 16 is 75. So this is exactly M inverse, which means, what did we do? What did we start with? We started with the integral from 0 to infinity, e to the minus tm dt, and we ended up with M inverse. Same as with numbers, where we started with this integral, e to the minus at dt, and we got 1 divided by a. And so this is really that matrix calculus in action. We're seeing that we have all sorts of these properties that behave with matrices, with integration, that we can play the same games with matrices. So it's really, really a cool thing to see about these matrix functions. Let's do another example where we can see some cool things with matrix functions. Let's recall the geometric series. I know it's been a while since I made you do any work on this idea of the geometric series. That was the following. I wrote it out as n starting at 0 and ending at infinity, x to the nth power, and this was equal to 1 divided by 1 minus x. So let's think about, if I replace x with a matrix, what would both sides mean? Well, on the left, we'd have something like this. M to the n power, and we're going to sum them up infinitely many. On the right, there's not really a notion of division. We should think about this as 1 minus a matrix inverse. And what is 1 in terms of a matrix? It shouldn't be the number 1. It should be the identity minus a matrix inverse. So that's how we'll translate the right-hand side. So let's go ahead and, given a matrix, let's compute M at 0, I over 2, negative I over 2, and 0. Or I suppose I could factor out a 1/2 and write this as 0, I, negative I, 0. Let's start with that matrix. Let's compute both. We'll compute the identity minus M inverse. And let's do this sum of m to the n, but let's just approximate it by the first 4 terms. So m0, m1, m squared, and m cubed. So there's going to be more terms that would show up, but let's just approximate it by those 4 and compare. Let's see if these ideas get close to each other. Let's see if they are approximately the same. The question becomes, how close will these be? So we want to see if our geometric series extends to matrices as well. So let's just go the identity minus m inverse. We don't even have to diagonalize or anything for this because the identity is 1, 0, 0, 1. We're going to subtract m, which is 1/2, 0, I, negative I, and 0. And we're just going to invert that matrix. And that's not too hard to invert, right? We can invert it as the matrix 1, negative I over 2, because I'm subtracting m, positive I over 2, and 1. And we have our 2 by 2 inverse formula. This is 1 over AD1 minus BC is plus I squared over 4. Well, I squared is negative 1, so that's 1 minus 1/4. This is 1 over 3/4. 1 over 3/4, also known as 4/3. And then we swap A and D, and we make B and C negative. And we have this as a matrix. Now maybe it'll make my life a little easier if I just pull it in and make everything numeric. 4/3 is 1.3 repeating, and then 4/6 will be the same as 2/3, right? 2/3, so this is actually 0.6 repeating I, negative 0.6 repeating I, and 1.3 repeating. So that's really the matrix that we're going to compare the bottom to. So let's go ahead and compute this collection. Well, the first matrix, M0, is just the identity. M1 is just 1/2, and I'm going to write it as I over 2 actually, and then just do 0, 1, negative 1, 0. M squared is going to be the previous quantity, this one, squared. So I'm going to have I squared, which is negative 1, over 2 squared, which is 4. And then let's square 0, 1, negative 1, 0. So 0, 1, negative 1, 0 times itself, 0, 1, negative 1, 0. We'll compute that later. And then M cubed is going to be I cubed, which is negative I squared, or sorry, negative I. It's I squared times I over 2 cubed is 8. And then we'll have 0, 1, negative 1, 0. 2 copies of that, 0, 1, negative 1, 0. 3 copies of that, 0, 1, negative 1, 0. So I'm just going to convert all of these and then add them all together. So I've got an identity here, which is the identity is 1, 0, 0, 1. And then let's compute the rest of those. So I've got 1, 0, 0, 1. And then I'm adding 0, I over 2, minus I over 2, 0. When I pull the I over 2 to every term here. And then I have a minus or a plus, and then I'll pull the negatives to the inside. But let's figure out what's going on here. My top left is going to be negative 1. My top right is going to be 0. My bottom left is going to be 0. And my bottom right is going to be negative 1. And that got multiplied by negative 1/4. So I'm really adding a 1/4 in both of these cases. And then if I'm computing all 3 of these out, I did just compute 2 of them as negative 1, 0, 0, negative 1. So I just need to multiply the last term by that. And then I have my minus I over 8 happening. This is going to give me minus I over 8. If I take all rows with all products, it looks like my top left is 0, my top right is negative 1, my bottom left is positive 1, my bottom right is 0. So it looks like I am adding a 0, and then I over 8. I'm adding negative I over 8 and 0. So if I combine all 4 of these together, element-wise, where does that take me? Takes me to, let's see, top left element, I have 1 plus 0 plus 1/4 plus 0. That's 1.25. I have 0 plus 1/2 plus 0 plus 1/8. 1/2 plus 1/8 is 0.625 I. I have 0 minus 1/2 plus 0 minus 1/8 is negative 0.625 I. And I have 1 plus 0 plus 1/4 plus 0 is 1.25. And so you can see, yeah, these are getting pretty darn close because 1.25 is pretty darn close to 1.3. 0.625 is pretty darn close to 0.6. negative 0.65 is pretty darn close to negative 0.6, and 1.25 is pretty close to 1.3. And so it's probably not too hard to believe that, yes, it seems like this with m to the nth power does converge to the identity minus m inverse. And there are some conditions that you technically have to add to make that a true statement, just like in the number case, you need to let a norm be less than 1. We haven't really developed a norm of a matrix here, but you can imagine it's like a norm of a vector space, because matrix spaces are vector spaces. The final thing I just want to mention as an example is that we can use these notions to give an idea of m to the 1/2, for example. But you'll recall that derivatives, something like d dx, is a linear map. And so we can actually use these notions to give us an idea of a 1/2 derivative. Whatever that means. And so there are really like well-defined notions of doing a half derivative. It's actually one of the first things I studied, even when I was an undergraduate. It's called fractional calculus. This is called fractional calculus. And we can even go much broader than that. We just have, we've opened Pandora's box, and we can do all sorts of things with derivatives too. So it's really a cool notion, everything we developed here. Anyway, I hope this was all really fun stuff that you've been seeing. It's really probably my favorite part of the semester. We'll move on by actually analyzing some differential equations in the next video. I'll see you then. Bye.